So, what if you could hold the power of a star right here in the palm of your hand? It sounds like science fiction, right? Well, today we're diving deep and unlocking the secrets of the atom. We're going to explore two of the most powerful forces in the entire universe, nuclear fission and nuclear fusion. Okay, so take a look at these two pictures. On one side, you've got a big pile of coal, the stuff that literally powered the Industrial Revolution. And on the other, just a small handful of these tiny pellets. Now, the real question here isn't about size, it's all about power. I mean, how is it possible that these little pellets can unleash millions of times more energy than that entire heap of coal? Well, the answer lies hidden deep inside the atom. The secret is all about unlocking the incredible power that's just stored inside the atomic nucleus. And so far, humanity has figured out two ways to turn that key. We can either split atoms apart, that's called fission, or we can force them together, which is fusion. So let's start with the one we've already gotten pretty good at. All right, first up, fission. You can think of it as the art of splitting the atom. This is the nuclear power most of us are familiar with, right? It's the technology that's been lighting up our cities for decades. So at its very core, fission is basically atomic demolition. Seriously, we take a big, heavy nucleus and we just shatter it into smaller pieces. But how do you even start something like that, this atomic demolition? Well, the trigger is actually just a single, slow-moving neutron. And because it doesn't have an electrical charge, it kind of acts like a ghost. It can just slip right past the atom's defenses and smack right into the unstable heart of something like a uranium-235 nucleus. So the uranium nucleus, it just absorbs this neutron. And that's all it takes. It's just enough to push it right over the edge, making it super, super unstable. It's kind of like adding that one last drop of water to a balloon that's already about to pop. And then, boom, in just an instant, that nucleus shatters. It creates two smaller daughter nuclei. In this case, we get barium and krypton. But here's the thing, this is not a clean break. These fragments, they're often radioactive, and that is a really crucial part of the story here. And this is where the magic really happens. The split releases this massive burst of energy, and this is the key part, more neutrons. And that energy? It comes from a tiny, tiny amount of mass being converted directly into pure energy. Just like Einstein's famous E=mc² equation predicted. It's like a set of atomic dominoes, really. Each atom that splits triggers the next one and the next one, creating this self-sustaining chain reaction that unleashes just incredible amounts of power. So, inside a nuclear power plant, this is exactly what's going on. That chain reaction is very carefully controlled to generate a ton of heat. That heat boils water. The steam from that spins a turbine, and that turbine generates clean, carbon-free electricity. Simple as that. Well, sort of. But harnessing a power that's basically a microscopic bomb, well, it comes with a catch. This amazing solution actually presents us with a pretty serious dilemma. Okay, so on the plus side, fission is a proven technology. We know how to do it. The reactions themselves are relatively easy to start and control, and the energy payoff, it's just astronomical. But just how much energy are we really talking about here? Get this, a single kilogram of uranium, which is about the weight of a pineapple, it can generate as much electricity as 2 million kilograms of coal. That's an entire train full of coal being replaced by something you could hold in your hand. The energy density is it's mind-boggling. However, there's a pretty big downside. Remember those daughter nuclei we mentioned earlier? Well, they are highly radioactive, and that creates a long-term waste disposal problem that, frankly, we're still trying to figure out. On top of that, the special type of uranium we need for this, it's a finite resource. It's non-removable. Once it's gone, it's gone. So this whole dilemma with fission has really pushed humanity to look elsewhere for an answer. And where did we look? To the heavens, literally. Instead of tearing atoms apart, what if we could build them up? This, my friends, is the power of fusion. It's the very same process that fuels our sun. Yep, nuclear fusion. And it is, for all intents and purposes, the exact opposite of fission. So instead of splitting these massive, heavy atoms, we're taking the absolute lightest atoms in the universe and forcing them to join together. Now, the most promising recipe for fusion, at least here on Earth, involves two special versions or isotopes of hydrogen. They're called deuterium and tritium, and the whole goal is to get them so close to each other that they can overcome their natural tendency to push apart and actually merge into one single larger nucleus. Okay, and I have to tell you, this is incredibly difficult to do. Why? Well, because both of these nuclei have positively charged protons inside them. And just like trying to push the same ends of two magnets together, they repel each other. A lot. So to get them to fuse, you have to somehow overcome that immense force by smashing them together at just unbelievable speeds. But if you can manage to overcome that force, the payoff is huge. The nuclei fuse together, and what do they create? Harmless helium, a spare neutron, and a burst of energy that, gram for gram, is even more powerful than fission. So what's the catch? Sounds perfect, right? Well, creating those kinds of speeds requires, let's just say, unimaginable conditions. To trigger a fusion reaction, you need to reach temperatures of over 100 million degrees Celsius. Let me say that again, 100 million degrees. That is more than 6 times hotter than the core of our sun. So, if, and it's a big if we can somehow overcome that monumental challenge, if we can literally build a star here on Earth, what does the future of energy even look like? Well, scientists are basically trying to bottle a star using 2 main approaches. The first one, which you see on the left, is kind of like building a magnetic cage. You use these incredibly powerful magnets to squeeze the superheated fuel, which is called a plasma, into a donut shape. This keeps it from touching the walls of the reactor, which would instantly vaporize. The second approach, on the right, is more like a tiny controlled explosion. We're talking about using the world's most powerful lasers to blast a tiny fuel pellet from all sides at once, crushing it until it just ignites. In this table really lays out the fundamental trade-off we're facing. On one hand, you have fission. It's the power of today, it's proven, it's commercially viable, but it comes with those heavy burdens of radioactive waste and limited fuel. On the other hand, you have fusion. This is the promise of tomorrow. It's a nearly perfect energy source with abundant fuel and clean byproducts if we can solve those absolutely massive technical challenges. And all of this leaves us with a really critical question for our energy future, doesn't it? We have a powerful but pretty flawed solution right now, today. So where do we focus our efforts? Do we invest in perfecting what we have, in making fission safer and cleaner? Or do we go all in and chase the incredible, potentially world-changing promise of a fusion-powered tomorrow? The answer to that question? Well, it's probably going to define the next century.